Just what exactly device turn off time and circuit turn off time. For reliable turn off of thyristor, always circuit turn off time is greater than device turn off time. Okay. Now we'll see, based on the turn off time, the thyristors or SCRs are mainly classified into two types. Okay. That is, based on turn off time, based on turn off time, based on turn off time, thyristors are classified into, the thyristors are classified into one is, it is classified into one is converter grade thyristors. Okay. Converter grade thyristors. This is one type, converter grade thyristors. Okay. Based on turn off time, the thyristors are classified into one is converter grade thyristors. For these thyristors, for this converter grade thyristors, the turn off time is, for this converter grade thyristors, the turn off time is less than or equal to 50 microseconds. Then it is called converter grade thyristors. If the turn off time is less than or equal to 50 microseconds, those thyristors are called converter grade thyristors. The less than or equal to 50 microseconds means 3 microseconds, less than or equal to TQ, less than or equal to 50 microseconds. That is, the turn off time is 3 to 50 microseconds. Those thyristors are called converter grade thyristors. Sorry, one point, not less than, sorry, concentrate. It's a converter, na? It's a converter grade thyristor. Okay, you take this is less than or equal to 50 microseconds. This you taken as, it's not a converter. This is a, first one is you take, this is a inverter grade thyristors. This is, sorry, concentrate. Okay. Inverter grade thyristors. If the turn off time is less than or equal to 50 microseconds, that is 3 to 50 microseconds, those thyristors are called inverter grade thyristors. Then turn off time is less, na? Then because of turn off time is less, then these are used for high frequency application. Used for high frequency applications. Inverter grade thyristors are used for high frequency applications. Because of less turn off time, if the turn off time is reduces, the time of operation is also reduces. Once the time of operation is reduces, then what the frequency of operation increases. Then these are used for high frequency application. Then these are costly thyristors. These are costly thyristors. These are high cost. Inverter grade thyristors are high cost. Then where you can use this inverter grade thyristors? What are the applications of inverter grade thyristors? Where you can use inverter grade thyristors? One is, these are used in choppers. Wherever high frequency application is required, in that application we can use inverter grade thyristors. And these are also used in inverters. These are also used in inverters. Then used in step up cycloconverters. Used in step up cycloconverters. Used in step up cycloconverters. This inverter gate thyristors used in step up cycloconverters. The another type of thyristors based on turn off time is converter grade thyristors. That you concentrate here. Converter grade thyristors. Converter grade thyristors or SCRs. Converter grade thyristors or SCRs. For this converter grade thyristor, turn off time is TQ is greater than 50 microseconds. Greater than 50 microseconds in the sense 50 microseconds to 100 microseconds or 200 microseconds. 100 microseconds or 2. This range is also already framed in GATE in competitive exam. For converter grade thyristors, what is the turn off time? It is given 50 microseconds to 200 microseconds. This is already framed in competitive exam. Then these are used for low frequency applications. Used for low frequency. These are less cost. These thyristors are less cost as compared to inverter grade thyristors. Then what are the applications of converter grade thyristor? Where we can use these thyristors? What are the applications? These thyristors are used in rectifiers. In rectifiers, we can use this converter gate thyristors. And these thyristors also used in AC voltage controllers. AC voltage controllers. These are used in AC voltage controllers or AC voltage regulators. These converter gate thyristors are used in step down cycloconverters. Step down cycloconverters, where low frequency operation is required. Okay, this about types of thyristors based on turn off time. Okay, this about inverter grade thyristors and converter grade thyristors. But one point to remember with respect to turn off characteristics of SCR, this note you remember. One is during turn off, ideally let assume that during turn off of thyristor, during turn off, ideally the characteristics of thyristor is given like this. During turn off, ideally the characteristics of thyristor is given like this. This is the characteristics of thyristor during turn off. This is characteristics of thyristor during turn off. If the characteristics are given like this, for any thyristor during turn off, if the characteristics are given like this, okay, now this is the characteristics of thyristor during turn off. Let this current is I1. Okay, this current is I1. This time is let this time is T1 and this time is T2 time. And the voltage across the thyristor is during turn off. The voltage across the thyristor is given like this. And this is V1. This is V1. Okay. This voltage across the thyristor is, this is V1. Now tell, this is the voltage across the thyristor is V1. Sorry, if you take like this one, this is T1 and T2. This I given, the characteristics are like this. This is correct. That this time is taken as T1 time and this time is given as T2 time. Okay. This is V1 and this is I1. Okay. In this case, what is the average power loss, you tell me? Directly I am giving that concept, you know how to do. Okay. Average power loss equal to, during which time power loss takes place? During T1 time, current is exist, but voltage is not present. During T2 time, both voltage is present and current is also present. Find the equation for this and find the current equation and voltage equation and integrate and substitute the limits. Then we can get average power loss equal to 1 by 3 V1 I1 F into T2. This is average power loss. How to do? So many concepts, so many problems I explained in the semiconductor switch concept. Okay, that is 1 by 3 V1 I1 F into T2. What is the storage charge or stored charge? You also calculate what is the stored charge in this equation, in this characteristic. Stored charge is equal to, I told this is current, this is anode to cathode current. Okay, we know that. How to calculate stored charge? Area under the current curve gives which one? Charge. Then what is the area under this current curve? 1 by 2 into I1 into T1 plus 1 by 2 into I1 into T2. This is two triangles now. This is one triangle. You find the area of this triangle. This is another triangle. You find the area of this triangle. Add those two. Then we can get. Then 1 by 2 I1, that is T1 plus T2. This is the stored charge. This is the average power loss. If you want average energy loss means you don't multiply with the frequency. You take only T2 time. Why I taken only T2 time? During T2 time only current is exist and voltage is exist. But during T2, T1 time, voltage is not present. Only current is present. Power loss is not takes place. Okay. This about in detail about what exactly dynamic characteristics, that is switching characteristics of a thyristor. What is the turn-on characteristics? What is the observation from the turn-on characteristics? What is the turn-off characteristics? What is the observation from the turn-off characteristics? All these concepts I discussed. And with this knowledge, we can answer any competitive exam based on this switching characteristics. Later on, based on this concept, I will explain some classroom workbook questions also. Later on, we will see. Okay, this about one concept in thyristor. Okay. Still now, with respect to thyristor, I discussed about what exactly static VI characteristics using modes of operation. What is two transistor analysis of thyristor? And I discussed about what are the turn-on methods of SCR, that is thyristor. And I discussed about switching characteristics, that is something about a dynamic characteristics. In the dynamic characteristics, what is turn-on characteristics and what is the turn-off characteristics. Okay. The another note you remember here, that I given one note. The another point you remember that you taken as a first one. I told both turn on and turn off time depends on junction capacitance. Under forward blocking mode, thyristor equivalent to one capacitance. Thyristor is equivalent to one capacitance. That's the reason why both, second note you remember, both turn on and turn off times, turn on and turn off time, both turn on and turn off time of thyristors, turn off time depends on junction capacitance. Depends on junction capacitance. Depends on junction capacitance. The third observation, if the SCR is operated at high temperature, the turn off time is increases or decreases? Increases. It takes more time for turn off. If SCR is operated at high temperature, if SCR is operated at high temperature, what happens? The turn off time is increases. Reason is same. Okay. Because of high temperature. What do you mean by turn off? Initially thyristor is under forward conduction mode. If the thyristor is under forward conduction mode, once it is operated at high temperature, it is having more number of charge carriers now. In order to remove the charge carriers, it takes more time or less time? More time. Then turn off time is increased. If SCR is operated at high temperature, turn off time is increased. Now you tell me, you compare on time and off time for any thyristor. Which time is greater? Yes, practically off time is greater than on time. Always the turn off time of thyristor is greater than turn on time. The turn off time of thyristor is always greater than the turn on time. Simple na? Turn on is nothing but you want to close one junction. Turn off is nothing but you want to open 3 junctions. Okay, that's why always off time is great. Just for understanding that I given a point, remembering purpose. That is, turn off time is greater than turn off time. Always turn off time is greater than turn on time. Okay. This about turn off characteristics or switching characteristics. Clear? Understood? Okay. Then you go for another important characteristics of thyristor. This concept comes under thyristor only. All these concepts. Okay. Still now I want to explain with respect to thyristor. I want to explain gate characteristics. Then I want to discuss what is the protection circuit of thyristor, what is the heating and cooling circuit of thyristor, what is series and parallel connection of thyristor, what is the commutation methods of thyristor. All these concepts comes under thyristor only. Okay. Then go for another important one is gate characteristics or SCR gate characteristics. That you see. SCR gate characteristics. What is the significance of gate characteristics of SCR? That you concentrate. Yes. See. What do you mean by gate characteristics of SCR means? These are the characteristics between VC versus IC. Gate voltage versus gate current. These are the characteristics between gate voltage versus gate current. Okay. What is the significance of drawing the gate characteristics of a thyristor? You know what is the significance of static VI characteristics now? Static VI characteristics explains the modes of operation. Turn on characteristics explains how the current through the SCR is changing from 0 to rated, how the voltage across the SCR is falling from rated to on-state voltage. Turn off characteristics explains how the current through the SCR is changing from rated to 0, how the voltage across the SCR is changing from on-state voltage to forward. All these are explained by dynamic characteristics, that is turn on and turn off characteristics. But what is the significance of this gate characteristics? What is the need of drawing the gate characteristics of thyristor? That gate characteristics explains to find operating point of a given gate terminal, given thyristor gate terminal. Told in the total SCR, gate is more sensitive element. If you apply the voltage less than the free specified voltage, then it will not trigger. If you apply the voltage greater than some maximum voltage, then gate will be damaged because it is operated at a very low rating. That's why for a given thyristor, at what voltage gate must be operated, at what voltage gate, at what current gate must be supplied. Means for thyristor, in order to design the gate voltage and gate current, it is required to draw the gate characteristics of a thyristor. That is the significance of drawing the gate characteristics of thyristor. Simply to find the operating point of a thyristor gate terminal, we are drawing the gate characteristics. How to find that operating point also I will explain. We know that in the thyristor, this is 4 layers. This P1, N1, P2 and N2. This is P1, this is N1, this is P2 and this N2. This anode terminal and this is cathode terminal. Then let initially the thyristor is under forward blocking mode. Thyristor is under forward blocking mode. Okay. Now we are supplying with gate voltage. This Vg is the gate voltage, Ig is the gate current. Gate trigger voltage and gate trigger current. Okay. Now this Vg and Ig is applied across PN junction. One PN junction we are applying. That's the reason why the gate characteristics of SCR is same that of diode characteristics, PN diode characteristics. Because we are drawing the characteristics between Vg and Ig, means this Vg Ig is applied across one PN junction. That's the reason why gate characteristics of SCR is same that of diode characteristics. Gate characteristics of SCR is PN diode characteristics. Is PN diode characteristics. Because we are applying Vg and Ig across PN junction. But even though PN diode characteristics, for our convenience, take voltage on y-axis, current on x-axis. But you know how to draw the PN diode characteristics now? In drawing of PN diode characteristics, you take an voltage on x-axis, current on y-axis, then we can draw the diode characteristics like this. But even though gate characteristics are PN diode characteristics, for our convenience, voltage is taken on y-axis and current is taken on x-axis. To draw the, even though these are PN diode characteristics, to draw the gate characteristics, Vg is taken on y-axis, Ig is taken on x-axis. We are interchanging the axis as compared to diode characteristics. As compared to diode characteristics, we are interchanging the axis. But by drawing the gate characteristics, to find the operating point of a given gate terminal, there is one theoretical concept is there, how to find the gate characteristics of a type. How to find the operating point of a given thyristor gate terminal. To find the operating point of a given thyristor gate terminal, let two reference thyristors, two reference SCRs. This is the theoretical procedure you follow, two reference SCRs. One is SCR1 is maximum doping concentration, like that we can consider one SCR. maximum doping. Beyond this, it is not possible. Like that, we consider the two reference SCRs. SCR2 is minimum doping concentration. SCR2 is a minimum doping concentration. SCR2 is a minimum doping concentration. That means we are considering the two reference SCRs. This PN junction is maximum doping. Beyond that, it is not possible. Like that, we consider one SCR. Another SCR is minimum doping. Below this, we cannot dope. Like that, we consider the two reference SCRs. This is maximum doping means what the cut-in voltage? Minimum cut-in voltage. For this one, minimum cut-in voltage. For this thyristor, this is minimum cut-in voltage. Minimum doping means this thyristor is having maximum cut-in voltage. Maximum cut-in voltage. This thyristor is having maximum cut-in voltage. First, draw the gate characteristics of a reference SCR. First, for these two reference SCR, first to draw the gate characteristics. This is the procedure how to find the operating point of a gate terminal, given thyristor gate terminal. First to draw the gate characteristics of a reference SCR. I told already, in drawing of gate characteristics, we are interchanging the axis. VG is taken on y-axis, IG is taken on x-axis. Current is taken on x-axis, voltage is taken on y-axis. Let SCR1 is maximum doping. This is minimum cut-in voltage. Then we get the characteristics like this. This is the minimum cut-in voltage. This SCR1, actually diode characteristics drawn like this, this is voltage. But you taken voltage is here, that's why this is the cut-in voltage. This is a cut-in voltage. For SCR1, we are drawing the characteristics like this. This is SCR1 cut-in voltage. SCR1, can represent like this. This is minimum cut-in voltage. Okay. Then you take another SCR. This is having maximum cut-in voltage. This SCR2 cut-in voltage. Okay. Now, by considering the safe operating area or safe operating region, then we get the characteristics like this. This is the gate characteristics for reference SCRs. This we can take like this, follow like this. Okay. Yes. This gate characteristics for reference SCRs. Okay. Let this is SCR1 characteristics. This SCR2 characteristics. Okay. This voltage is maximum gate voltage, VCM. This current is maximum gate current, ICM. Okay. This is S, represent like this. This one is represented like this. S, this point O, okay, this is point O, and this is A, this point is A, this point is taken as A, and this point is, you take OY, okay, corresponding to this, you take this is OX, okay, this you take OX point, okay, correspond this touching point, you take OX point. Understood? This is Ox. Okay. Then this Ox equal to minimum gate current. This is IGMX. This is VGMX. Oy equal to minimum gate voltage. Okay. This OA is non-trigger voltage. Non-trigger voltage. Okay. Non-trigger. These are the reference. This you taken as a reference. Okay. This you taken as a reference. Okay. Now let's assume that for given SCR you want to find the operating point of a gate terminal. Okay. You want to find the operating point of a gate terminal. Okay. Then how to find the operating point of a gate terminal for given SCR means, for operating point of a gate terminal for given SCR means, for this, you take this one is for this. Okay. Let this point is O, this is Y. Okay. Then this point is taken as a this is A means this you taken A now. Then this is okay. This you taken as a B. This point is B. This is C. This is D. This is E. This is F. And this is G. Then you take some point is H that I will give. Okay. B, C, D, E, F, G. Okay. Now this is the given thyristor. This is the given thyristor. Okay. For this thyristor, supply voltage is Vs. Gate supply voltage is Vs. For this is the given thyristor. And gate source resistance is Rs. Gate source resistance is Rs. Okay. Then this is the given thyristor. Okay. Then let this current is gate current IC. Then gate voltage is Vc. Then you apply the KVL for this loop. If the KVL is applied, what we can get? We can get Vs equal to Vc plus Ic into Rs. Vs equal to Vc plus Ic into Rs. Where Vs is gate supply voltage. Gate supply voltage. Gate supply voltage. Okay. Vc is gate trigger voltage. Gate supply voltage is different and gate trigger voltage is different. Gate trigger voltage. Okay. Ic is gate trigger current. Ic is gate trigger current. Gate trigger current. Okay. Rs is gate source resistance. Gate source resistance. Gate source resistance. Clear? Now this is the given SCR. Now draw the gate characteristics of given SCR. One SCR is maximum doping, another SCR is minimum doping. You take any another SCR whose characteristics are in between 1 and 2 na? Then if you draw the gate characteristics of given thyristor, then whose doping concentration in between 1 and 2 means the cutting voltage also in between 1 and 2, then you get this is the gate characteristics of given thyristor. This point is taken as A, this is taken as a B, this is H. Then the safe operating area is B, C, D, E, F, G, H, B is the safe operating area. In this, which is the safe operating area? B, C, D, E, F, G, H, B is the safe operating area or safe operating region. So, okay, this about given. Now you want to find operating point. For this SCR, how much gate voltage you want to apply? How much gate current you want to apply? That gate voltage and gate current may not cause us non-triggering, may not cause us damage. Like that, how much VC we can design, how much IC we can design. That is nothing but finding the operating point. Okay. Yes. Now, to find the operating point of a gate terminal, first locate supply voltage on y-axis. Let this is the supply voltage. And locate Vs by Rs on x-axis. Vs by Rs means current na? Locate Vs by Rs on x-axis. Then join these 2 points. Then join these 2 points. Then this line is called load line. Load line. Okay. Then the intersection of given SCR gate characteristics and load line gives the operating point of a given thyristor. Then this operating point is always in between 1 and 2 only. If this operating point is below 1, then that SCR will not trigger. If that operating point is above 1, above 2, then SCR will be damaged. Okay. Like this, we can find the operating point of a given gate thyristor gate terminal. This line is called load line. This is given SCR gate characteristics. Like this, we are finding the operating. How to find the operating point is not important for competitive. This is only concept only. Okay. But after drawing this characteristics, after finding the operating point, from this I want to list out some points. Those points are very, very important for any competitive point of view. Now I will say I want to list out the points. Okay. That this formula you concentrate. Along this I want to list out some points. That you will see. After drawing the gate characteristics, tell me. Concentrate on this characteristics. Tell me. Then the slope of the load line is a positive or negative? Falling slope na? Falling slope means negative. Before that, one point to remember, that is the intersection of load line and given SCR gate characteristics. Given SCR gate characteristics gives which point? Gives operating point S. Operating point S. That point you remember. This curve is called PGAV curve, average gate power dissipation curve. This is a safe operating area curve. That is the average gate power dissipation curve. Then slope of the load line is negative. Slope of the from the gate characteristics. Slope of the load line is negative. Load line is negative because it is a falling slope. What is the slope? Slope equal to y-axis coordinate by x-axis coordinate. What is the y-axis coordinate? Vs. For this, y-axis coordinate is Vs. What is the x-axis coordinate? Vs by Rs. It is a negative slope, na? Minus. That is minus Rs. That means, therefore, slope of the load line indicates in a gate characteristics. Slope of the load line indicates. Slope of the load line indicates. Slope of the load line indicates which resistance indicates gate source resistance. Gate source resistance. Slope of the load line indicates gate source resistance. Yes. Third observation. Very, very important points. Slope of the load line indicates gate source. For example, if the slope of the load line is minus 130 volts per ampere, then the source resistance equal to source resistance is how much? That is the gate source resistance, 130 ohms. You don't take minus, where negative indicate the falling slope, then 130 ohms. If the slope of the load line is 130 volts per ampere, then the gate source resistance is 130 ohms. Okay. Then third observation. Tell me. the slope of the gate characteristics, or before that, gate characteristics are practically linear or non-linear. It's a non-linear characteristics. The gate characteristics of SCR is non-linear characteristics because it is a diode characteristics. Yeah. Third one, gate characteristics is non-linear. Gate characteristics of SCR is generally it is a non-linear. Gate characteristics of SCR is non-linear. Next, slope of the gate characteristics is positive or negative? It is a rising slope na, all the gate characteristics are rising slope na, positive slope. That is the slope of the gate characteristics. Slope of the gate characteristics is positive. Is positive. Yes, fifth observation. We know that this circuit is given like this now. This is gate source resistance. Gate source resistance is RS. This is gate trigger voltage. Gate trigger voltage. And gate trigger current is IC. This is IC. And this is VC. Okay. This is VS. For example, if RS is reduces, what is IC? Increases. If IC is increases, what is the turn on time? Reduces. Okay. That means if you design the gate source resistance with minimum value, the turn on time is reduced. Now the question is, to reduce the turn on time, what is the minimum value of source resistance, gate source resistance we can design? But you don't make completely zero. If you make completely zero means because of high gate current, SCR may be damaged. Now the question is, you want to reduce the turn on time, but the thyristor, that gate terminal may not be damaged. Without damaging the gate terminal, to reduce the turn on time, then how much value of RS can connect? What is the minimum value of source resistance we can connect? Then how to calculate means, this is calculated from the characteristics itself. Tell me, if RS is reduces, what about IC? Increasing. IC is increasing means the characteristics are shifted like this now. Characteristics are shifted in the right direction now. We are not changing supply voltage. We are changing only gate source resistance. For different values of source resistance, if you draw the characteristics, then that characteristics will be shifted like this. At a particular value of RS, this load line is tangent to PCAV curve. Then slope of this tangent gives which value? RS minima. Then beyond this, we cannot reduce RS value. Then because of high gate current, the gate terminal may be damaged. Now the question is, then sixth observation. To reduce turn on time, to reduce turn on time, to reduce turn on time, turn on time, to reduce turn on time. If to reduce turn on time, how much value of minimum source resistance is connected? What is the minimum RS? How to calculate minimum RS? Okay. Then if the load line is tangent to PCAV curve, if the load line is tangent to the PCAV curve, average gate power dissipation curve, then the slope of the tangent gives, then the slope of tangent equal to, then the slope of tangent, then the slope of tangent gives which value? RS minimum. Then the slope of the tangent gives the RS minimum. So okay, like this we calculate, like this we can design minimum value of RS, minimum value of RS to reduce which time? Turn on time. Okay. But generally, the gate characteristics of SCR is which one? Non-linear. Because of which characteristics? Diode characteristics. The gate characteristics of SCR is a diode characteristics. That's why we taken as a non-linear characteristics. Then tell Ideally, let assume that. Ideally, let assume that. Ideally, let assume that. Ideally, let gate characteristics are, but practically it is a non-linear. Let gate characteristics are, passing through horizon. Let this is VC and this is IC. Gate characteristics are passing through horizon. This is VG and IC. Then what the slope of gate characteristics? Then slope equal to VG by IC. If the gate characteristics are given like this, the gate characteristics of thyristor is passing through horizon. If it is a linear characteristics, then the slope is defined as Y by X. Y axis is VG, X axis is IC. But point to remember, slope of the load line only indicates the gate source resistance, not the slope of the gate characteristics. Slope of the load line only indicates the gate source resistance, this one, but not the slope of the gate characteristics. Slope of the gate characteristics will not indicate gate source resistance. Okay, this about what exactly, how to draw the gate characteristics of thyristor, then how to find the operating point. From that operating point, then we can list out some points. These points are important. How we are drawing the gate characteristics, that only concept, not important for competitive point of view. From that, we are list out these points now. These points are important for any competitive point of view. Okay. Then I want to extend this concept, important for competitive point of view, already framed in so many competitive exams. This circuit is called, this is gate current, IC is the gate current, then VG is the gate trigger voltage, okay, VS is the gate supply. Then this total circuit is called gate triggering circuit. This total circuit is called, which one? Gate triggering circuit. This is called triggering circuit. Here we are giving this triggering circuit is supplied with DC voltage. Then we also give the AC triggering. Then based on the gate supply voltage, the triggering methods are broadly classified into two types. One is DC triggering and other one is AC triggering. Now I want to explain what is the DC triggering, what are the drawbacks with the DC triggering. Then whatever the drawbacks are present in DC triggering, that can be overcome by using the AC triggering. But in AC triggering, again, pulse triggering is more preferable. What exactly pulse triggering? What is the advantage of pulse triggering? That concept also I want to discuss. These two are very important concepts. Okay, this is clear? Okay. Now we'll see what is the types of triggering based on supply. Types of triggering based on supply, gate supply voltage. Yes, go with types of triggering. Types of triggering based on types of triggerings based on gate supply. Based on gate supply. Based on gate supply. Okay. Based on gate supply voltage, the triggering methods are broadly classified into two types. One is DC triggering and DC triggering. Another one is AC triggering. AC triggering. But in AC triggering, mainly concentrate on pulse triggering. We'll see what exactly DC triggering. Yes. A DC triggering means a continuous DC supply is connected across gate cathode terminals. That means if it is a thyristor, okay, this is gate source resistance RS and this is Vs and this current is IC and this current is VC. That is a continuous DC supply is connected. DC supply is connected across gate cathode terminals. Like this we are connecting. But here once we are using DC triggering means we are not making on and off of pulses. Continuously we are connecting the supply. Continuously we are connecting the supply means it adds additional power loss. That is one of the drawback of DC triggering. That is because of continuous supply it adds additional power loss. Okay. Then what the drawbacks with the DC triggering means? Because of continuous supply, it adds additional power loss. Because of continuous supply, it adds additional power loss. Okay, that is one drawback. Second one, is there any isolation between the power circuit and gate terminal? This is the gate supply we are giving. This is the gate terminal. There is no isolation between the gate terminal and power circuit. Means if any fluctuations in the gate supply that directly affects the gate terminal, then gate will be damaged because gate is more sensitive. Understood? That's why there is no isolation between. There is no isolation between gate terminal and power circuit. There is no isolation between gate terminal and power circuit. That isolation is provided in the AC triggering. That you will see. There is no isolation between gate terminal and power circuit. Okay. Another one is at a time only one thyristor is triggered. That is at a time only. But that is not the case in the case of AC triggering. That AC triggering we can trigger at a time more than two thyristors are. Two or more than two thyristors also we can trigger. But at a time only one thyristor is triggered. In DC triggering, the average gate power loss PGAV equal to PGM equal to average and maximum gate power loss is same. That is equal to VG into IC. That is the average gate power loss equal to maximum gate power loss equal to VG into IC. This what exactly DC triggering. This is the drawbacks with the DC triggering. To overcome this, now we are using AC triggering. But in AC triggering, the pulse triggering is important. That we will see in the session. Next section. It's clear? Okay. These are the drawbacks with the DC triggering. In DC triggering, average gate power loss and maximum gate power loss is same. That is, average gate power loss equal to maximum gate power loss means high power loss na. That is the problem with direct, that is DC triggering method. Then you go for next concept is AC triggering, that is nothing but a pulse triggering. In the next session, we'll see continuation of this one.